chromatography or gel pull technique in the field of polymer chemistry. Where polymer, everyone knows polymer is a macromolecule. It has not a specific molecular weight is not there. For a polymer, we always talk in terms of molecular weight distribution, MWD, molecular weight distribution. And there are different types of molecular weights available for a polymeric material, like number average molecular weight, Mn, weight average molecular weight, MW, Z average molecular weight, MEZ, viscosity average molecular weight, MV. There are different molecular weights can be defined. All these, and polydispersity, what is the ratio of MW by Mn, all these can be precisely found out using a GPC. It is a wonderful technique for characterization of polymers. In polymer chemistry, it's a widely used technique, GPC, gel permeation chromatography. Then we are using a liquid mobile phase. We are going to use a ion exchange resin as the stationary phase. And the principle of separation is based on ion exchange. It can be either cation exchange or anion exchange. And the technique is known as IEC, ion exchange chromatography. Then the last one, I think students must be knowing this. We are going to use a mobile phase as a liquid, and stationary phase is a thin plate, maybe an aluminum plate or a glass plate coated with a uniform layer of silica. And silica, everyone knows it is an adsorbent material, and the principle of separation is adsorption. And the technique is known as TLC, thin layer chromatography. It's a very, very simple technique. It's an but at the same time, it's a very good technique for the initial screening of a given sample, TLC. And now TLC has become automated. We talk about HPTLC, high performance thin layer chromatography. Now, why we are going to use GC compared to HPLC? In the case of GC, analysis time is much shorter. So we have short analysis time, and we have different stationary phases available. Compared to LC, the number of stationary phases available in the case of LC is limited. Whereas in the case of gas chromatography, number of stationary phases available are plenty. So many stationary phases are available. So we have the freedom to select the right type of stationary phase for our sample. There are different types of detectors for detecting the compounds coming out of the column. And it's a very easy operation. It's a simple technique, not very complex and complicated. And what are the goals of carrying out a GC analysis? To separate mixtures of organic compounds. When I say this, this can be slightly confusing. You may ask me why GC cannot be used for inorganic compounds. I told you what is the limitation. Just remember the limit. The number one limitation of GC. GC is applicable to only volatile compounds. Most of the inorganic compounds, inorganic salts or oxides or chelates, whatever, they are all totally non-volatile compounds. They cannot be handled by GC. They cannot be analyzed on a GC. So that is why most of the inorganic compounds are out of question of GC analysis. At the same time, we can also use GC for certain very, very small molecules of inorganic compounds. Gas analysis. Think of atmospheric air. What is the composition of atmospheric air? It's approximately 79% nitrogen, 21% oxygen, and then the other things are the minute amounts of carbon dioxide, or carbon, water, all those. But the major components are nitrogen and oxygen. Okay, 79, 21. So if I have a GC at room temperature, and if I have a certain column, it's known as a 5 molecular C5A column, and if I got a thermal conductivity detector, without heating, because sample is already air, it's already in the gaseous form. If I introduce the sample into my column, I can get two beautiful peaks of nitrogen and oxygen. That means I have separated atmospheric air into nitrogen and oxygen. It's an example of inorganic analysis. They are inorganic gases. I can think of separating carbon monoxide and carbon dioxide at very, very low concentration. Extremely important application in petrochemical industry and fertilizer industry. Carbon monoxide, carbon dioxide separation in some of the gas streams. A very, very critical analysis. We can use GC for that. It's an inorganic separation. But then all these compounds are already in the gaseous form. So for us, it is very easy. So there are certain very few samples like gas analysis where we can use GC for inorganic separation. Other than that, the other inorganic compounds and all those compounds are out of bound of GC because they are totally non-volatile samples. At the same time, most of organic compounds are volatile under GC condition. Even here, I have to make a point. even organic compounds, when I'm talking about organic compounds, I am talking about low molecules, small molecules, not low molecules, small molecules. I mean, any sample molecule having a maximum molecular weight of approximately 600 only can be analyzed on GC. Suppose if I got a organic compound whose molecular weight is more than 1000, we talk about proteins and peptides and all those separations. We cannot use GC because there are high molecular weight compounds. We call it as a macromolecules. We cannot use GC for that. We can use LC for that. So we are, even when we talk about organic compounds, we are talking about small molecules. Okay, then detect, individual, analyze. We can identify and quantify using reference standards. GC can be used as a qualitative analytical technique and a quantitative analytical technique. But then for identifying a compound and quantifying that compound, we require reference standards. This is equally applicable to LC also. A typical GC system, a GC system is comprised of 5 main parts. One is the flow controller, because what is the mobile phase? We are going to use a gas. So we are going to use a gas like say nitrogen or hydrogen or helium. That's a normal carrier gas we are going to use. That's a mobile phase for us in DC. And what is the source of gas? It is a pressurized cylinder. You can see a big gas cylinder we are going to use, which contains a pressurized gas like nitrogen. And the pressure of the cylinder is very high. A full pressure cylinder, full cylinder pressure is approximately 140 to 160 kilograms per square centimeter. It's a very, very high pressure inside. So we should have a mechanism by which can control the pressure. And normally we apply pressure of around 6 to 7 kilograms per square centimeter on the GC system. So for which we require a flow controller. And then we have a injection port, because in the case of chromatography, GC or LC, we are going to inject the sample using a syringe. We have to inject a very, very small quantity of the sample using a syringe. So injection port is the place where we are going to introduce the sample. And when we introduce the sample into the injection port is heated. As a user, you have to optimize the temperature of the injector. What is the temperature required for the injector so that my sample immediately turns into vapor form? So that you have to optimize. This temperature can vary from sample to sample. In lot of optimization process, lot of optimization steps are involved in GC. So injection port temperature is to be optimized by you. And then when you are introducing such a small quantity of the sample into a heated injection port, it will vaporize, and your carrier gas is also coming, your mobile phase, we call it as a carrier gas. Mobile phase is the same as carrier gas. And that is also coming to your injection port, and your injection port, your sample vapor and the carrier gas will mix together and they will go to the column. And column is put inside an oven, because column is also to be heated separately. Okay, so the actual separation will take place inside the column, and from one by one, the compounds will start coming out of the column. And when they come out of the column, they will go to a detector, and detector is also to be separately heated. And the detector is going to give an electrical signal, and that is going to be processed by your software, PC. So in the case of GC, you have 3 different heating zones, heated zones. One is injection port is heated separately, independently. Column is always inside an oven. Oven has got its own heater. And the detector is also to be heated separately. So detector also has got its own heating mechanism. So 3 different heated zones are present inside a GC. So this is how a normal GC looks like. It's just a diagram for the students to understand. So there is a cylinder, that's a carrier gas, that's a mobile phase. And as I told you, it's at a very high pressure. We have a regulator on that. We have to regulate the pressure. And there is a flow controller. And we adjust the pressure of approximately 6 kilograms to 7 kilograms per square centimeter on the equipment, on the GC. And this gas is coming to the injection port. You can see the injection port there. And there is a microliter syringe with which we are going to introduce the sample. We are going to inject the sample. A very, very small quantity of the sample is required. we don't have, we should never introduce a large quantity. We are going to inject extremely small quantity of sample. And the sample quantity is always in terms of microliter. Many times now we inject only 0.2 microliter, 0.5 microliter, or at the most 1 or 2 microliter. More than that, it becomes a huge quantity for GC. We never do that. Such a small quantity of sample, either you can inject it manually yourself, or nowadays people prefer a auto injection. We have auto injectors. That means the injection will take place automatically. Okay, so when it goes in, when it is injected in the injection system, the injection port is always at a high temperature, and the sample will vaporize. It will get converted into vapor, and your mobile phase, that is the gas, carrier gas, is also coming there. They together will go to the column, and you are seeing the column is put inside an oven. And I will say column is the heart of the system, because column is going to give you the separation. Ultimately, what separation you are getting for your sample is because of the column. So column is the most important part of the system. So when the sample is moving to the column, different compounds will get separated inside, and one by one, the compounds will start coming out. That means one compound at a time. After some time, another compound will come, so that different compounds will come out of the column at different times. And when it comes out of the column, it goes to a detector, and this detector is also heated, and the detector is going to give an electrical signal, and that is processed by your software, and it is and when a compound is coming out, the detector is going to give an electrical signal, and that is converted into, it is represented as a triangular peak. So that means one peak represents one compound. So if there are 3 compounds in your sample, and they are coming at 3 different times, say maybe like 5 minutes, 7 minutes, 12 minutes. So 5 minutes you will get a peak, triangular peak, that is representing compound number 1, which has come, that has come out, the first compound. After some time, second compound will come, you will get again a triangular peak, and the third compound comes out, you will get a third triangular peak. So one peak represents one compound that is coming out from the column. This is again a same way. I mean, this is, I mean, I'm not going too much into the hardware system. So this is one more diagram I am showing here, because you can see on the left-hand side, there is a cylinder which is called a carrier gas. That's a mobile phase. And please note that the carrier gas is always connected to the injection port. And on the right-hand side in the slide, you can see there are 3 more cylinders. One is a hydrogen cylinder, one is a air cylinder, and one is called a makeup gas cylinder. And these 3 cylinders are connected to the detector. You can very clearly see all the 3 cylinders are connected to the detector, whereas your mobile phase, that's a carrier gas cylinder, is connected to the injection port. So the other 3 gases like hydrogen, air, and makeup, they are known as detector gases, and they are connected to the detector. And why this hydrogen and air are required, you will understand when we go forward. So we have different cylinders will be required depending upon what is the configuration of your GC system. Okay, certain detectors will require a hydrogen and air flame. So that's why we require a hydrogen cylinder and air cylinder. And carrier gas cylinder is required everywhere. So that is the mobile phase. So that is always required. So please note that carrier gas is always connected to the injection port, and detector gases, which are also called auxiliary gases, they are always connected to the detector port. Now, what is the zone migration? This is the essence of chromatography. Whether you are talking about gas chromatography, whether you are talking about liquid chromatography, the separation what you are getting inside a chromatography column is because of mechanism of zone migration. What does this mean? I'll just read the sentence, and for the students to understand this very carefully, that is the basic mechanism by which the separation is getting effected in a column. Chromatography separation is due to the differential migration rate of components in the mixture. So what does this mean? I'll just make a very, very simple example. Suppose you have got a binary sample. Binary sample means you have got a sample which contains 2 different chemical compounds, A and B. Both are 2 different chemical compounds. One is compound A and one is compound B. And you have a chromatography system. So consider it as a HPLC system or consider it as a GC system. And any chromatography system, there is a column. The column contains what? Column contains a stationary phase. I told you before, stationary phase is always inside the column. And stationary phase is also nothing but a chemical compound. It's nothing but a chemical compound, stationary phase. Okay. Now imagine you introduce a very small quantity of your binary sample into the column, either in HPLC or in GC. So when the sample goes inside, there is a stationary phase which is also a chemical compound. So there will be physical interactions between the components in your sample and the stationary phase. You remember what I told you, there are only physical interactions and no chemical reactions taking place inside a chromatographic column. Only physical interactions. So there will be a lot of physical interactions between the compounds present in your sample, that is compound A and compound B, and the stationary phase, which is also chemical. So out of these two compounds, you imagine compound A likes the stationary phase. I mean, they have a liking to between each other. They like each other. That means there is a degree of affinity. There is a larger degree of liking. So that means since compound A likes the stationary phase, it would like to remain inside the column in that stationary phase for a longer time because they like each other. There is an affinity between them. So they want to be together for quite some time. At the same time, the second compound, compound B, does not like the stationary phase. There is no affinity. There is no bonding. Absolutely no liking toward the stationary. So what will happen? Compound B, he doesn't want to remain inside the column for a long time because it doesn't like the stationary phase. It wants to come out faster. If I don't like somebody, why should I remain with him for a longer time? I would like to walk out. The same way, the compound B, which doesn't like the stationary phase, would like to move out faster, and that means it is going to move at a faster speed because it wants to come out faster. At the same time, compound A, since it is liking the stationary phase, it is spending a little more time inside the column, and it will move very slowly, and finally that also will come out, but it will come out later, much later. So that means a compound which has larger degree of affinity toward the stationary phase will move at a much slower rate, and a compound which doesn't have that much affinity toward the stationary phase will move at a greater speed. That means depending upon the difference in the degree of affinity or depending upon the degree of liking, these two compounds are moving at two different rates. That is, their migration rates are different. And that is why one compound is coming at one time and another compound is coming at a different time. And the difference in time is basically because of the difference in the degree of affinity of each compound towards the stationary phase. Okay, so that is what is known as differential migration rate. Now, when I talked about a binary compound, it's very easy for us to optimize the conditions because my sample only contains two different compounds A and B. If I take out the same example, what I told you, a perfumery compound, a sample may contain more than 100 different chemical compounds. And if I want to separate all these 100 different chemical compounds through a column, what is required is all the 100 compounds should move at 100 different speed. Otherwise, many compounds will come together. That is what is known as coelution in chromatography. Means two different compounds are moving at the same speed. They will come out of the column at the same time. That is what is known as a coelution. That means your column is not able to separate these two compounds. Coelution can be a problem in chromatography. So that is why you should be very careful while selecting the column. So you should know what is the column chemistry and you should know what is the sample chemistry. There should be a proper match between these two. Sample chemistry and column chemistry should match. Otherwise, you will not get the desired separation in any type of chromatography. So this is the mechanism of zone migration is the essence of getting a proper separation in chromatography. So when you are introducing a sample into a chromatography system, there is a stationary phase, there is a mobile phase. Your compounds present in your sample gets distributed between these two phases. And that means the compound gets distributed between mobile phase and stationary phase. So at any given point of time, there is a dynamic equilibrium between the molar fraction of your sample in the mobile phase and the molar fraction of your sample in the stationary phase. Okay, now what is your intention? Whatever has gone inside the column, it has to come out. That's a very basic thumb rule in GC or LC. Whatever goes inside has to come out. So when the sample is getting distributed between the mobile phase and stationary phase, well, ultimately our aim is to take out the entire sample, entire amount of sample from the column. It should come out and should go to the detector. And that is your optimization process. So when you're optimizing a GC condition or an LC condition, you are trying to, by optimizing the conditions or parameters, you are trying to shift the equilibrium from the right hand side to the left hand side. That means you are trying to take out as much as possible of the sample from the stationary phase to the mobile phase so that it can flow out of the column, go to the detector and gets detected. That's your optimization process. It's not like a UV analysis or an IR analysis. Here, a lot of parameters are to be optimized. It's a time-consuming job. But sometimes for method development, method optimization, we take days together. It is not a 1 hour job, or sometimes it may not be a 1 day job. Sometimes it may take days together to optimize a method. If it's a very complex method, it takes a lot of time to optimize. Now, this is just for the understanding of the students. So I have a column. I have introduced the sample to the column which contains 3 different compounds. And each compound is represented by a certain shape. There's a triangle, there's a circle, and there is a square. Each one represents one type of compound. So then your mobile phase is also passing to the column. So you can see they are getting separated. And what is your observation? The triangle is at the front. The triangle compound is at the front. And the circle compound is at the back. And the square is in the middle. So from this, what is your information? What is your inference? The compound represented by the triangle has the least affinity towards the stationary phase. That is why it is moving faster and coming out of the column first. At the same time, the compound represented by the green circle has the highest degree of affinity toward the stationary phase, and that is why it is moving at the slowest speed and will come out last. So depending upon the difference in the degree of affinity, you can see different compounds are getting separated inside the column and they are moving at different speeds and coming out of the column at different times. That's a very, that's a real essence of chromatography separation. Now, I just want to spend a minute. I'm not going into details about this. This slide itself I can discuss for a long time, but time will not permit me. Evaluation of columns, because as I told you, column is the most important part of the equipment. I'm audible properly? Hello.
Yes, sir. Yes,
okay.
sir. Audible.
Okay. So why I'm taking this slide, because column is supposed to be the heart of the system. Now, column, please understand, column is also a consumable item. It is not a permanent thing. At one point of time, you will have to replace the column. So there is a certain life for the column. When we go to industry, many times people ask us, if I purchase a column today, how many years I can use it? Very, very difficult question to answer, because column life depends on so many factors. It is not practical to quantify the column life. It depends on so many factors. It depends on the type of sample itself, how many samples you are going to analyze, how much care you take about column. There is something called column care. I mean, so as a user, you have to take a good care of the column. All these will matter in determining the life of the column. So, but one point of time, column will have to be replaced. So many times when you go to industry also, or many times in your laboratory also, if you are having a chromatograph, people talk about column efficiency. Somebody may come and say, my column is very efficient. And what is meant by column is very efficient? What is meant by column efficiency? It is always related to the sharpness of the peak. Means every chromatographer would like to get a very, very narrow and sharp peak. And if your column is able to give a very sharp peak, that means your column is very efficient. I don't want a very broad peak for me. Nobody would like to have a very broad peak in chromatography. Because if you are getting a broad peak, there are a lot of problems. Your reproducibility can be a problem. Your quantitative estimation results can be a problem. A lot of problems you'll have. So the answer is possible, and resolution can be a problem. So what we want is always a very narrow and sharp peak. And when the column is able to give a very sharp peak, your column is supposed to be a very efficient column. So column efficiency is always related to the sharpness of the peak. And there is a variable n value, capital N. It is known as number of theoretical plates. Or there is another parameter, HETP, height equivalent to one theoretical plate. And these are the variables we actually use to define the column efficiency. There are certain calculations also, but I think, I'm not going into those because time will not permit me. So we say, if the n value for a column is very high, that is number of theoretical plates, capital N, is the value for n is very high, that means your column is very efficient. Similarly, we say the value of HTTP is very, very low for a column, then also we say the column is very, very efficient. So a very efficient column will have a very high n value and a very low HTTP value. And as you start using the column over a period of years, depending upon the type of samples, how many samples you are analyzing, this n value will keep on decreasing. So when it starts decreasing, after some time, you will have an observation that initially when the column was brand new, the peaks were very sharp. Now the peaks have become broader and broader. That means your column is losing efficiency, and that is a time you have to think of replacing the column. It can take 1 year, it can take 2 years, it can take 3 years, all depends. We cannot quantify that. I've seen some people, users using column for almost 4 years or 5 years without any problem. But the samples are very clean samples. At the same time, I've seen a user who is changing the column twice in a year because his samples are very crossy samples. So the major parameter is the type of the sample itself. So that has got a very prominent effect on the life of the column. There is something called solvent efficiency, or it is also known as a selectivity factor. That means if you have a certain column, when I say column, I am always referring to stationary phase. So when I am having a certain column, and if I have got two compounds in my sample whose boiling points are very close by, or the polarities are very close by, whether this column is able to separate these two compounds or not. And that is the information I will be getting from my selectivity factor. Okay. And there is also another factor called as peak symmetry. I don't know, somebody must have told you about tailing peak. Tailing factor. But ideally speaking, your chromatography peak should be like an isosceles triangle. Isosceles triangle, everyone knows, every student knows what is an isosceles triangle. If you drop a perpendicular from the peak maximum to the baseline, this perpendicular will divide the peak into two equal halves. Width of first half will be exactly equal to width of second half. That's called a symmetrical peak. That's like an isosceles triangle. And every chromatographer would like to have his chromatography peak also to be symmetrical. That means if you divide the peak by a perpendicular, it should divide it into two equal halves. That's called a symmetrical peak, but many times you don't get it. And your observation is many times you get a tailing peak. Tailing peak means when you're dividing the peak by dropping a perpendicular, your second half width is slightly more than the width of the first half. And then we call tailing. And tailing is an accepted phenomenon in chromatography. Even pharmacopoeias also accept tailing to a certain extent. But beyond that, it is not acceptable. So you have to, if the tailing is coming too much, then you have to find ways and means by which you can reduce the tailing. And we have certain process by which I try to reduce the tailing. So tailing factor is there. So that shows the symmetry of the peak. So all these parameters are basically pertaining to the column. These are all applicable to GC column. These are all applicable to HPLC columns also. Ultimately, you want a very good resolution. Everyone talks about resolution because resolution gives information. Suppose your sample contains 10 different chemical compounds. If the resolution is poor, you will not be able to see all the 10 compounds very clearly. Some may be partially separated. Then the resolution is very poor. If the resolution is very, very good, then you'll be able to see all the 10 different compounds as 10 clearly separated peaks. So resolution is the most important thing. Finally, what you want is a very good resolution for your sample components. And there is a universal equation that is what is shown there. And this resolution equation is influenced by 3 different factors. One is the efficiency. I told you n value, efficiency of the column. There is another factor known as capacity factor of the column, and then selectivity factor alpha value. And these 3 factors will ultimately decide what is the resolution, what you are going to get in a chromatographic separation. So to sum it up, I can say, but normally when we go to industry also, we tell the customers, we tell the users to get a separation by optimizing the conditions, you should get a separation at least 1.5. You can see on the slide on the extreme right-hand side, R is equal to 1.5. That means the resolution is equal to 1.5. If I'm getting a resolution is equal to 1.5, that means my peaks are properly separated on the baseline. It's a wonderful separation. You can see that 2 peaks are well separated on the baseline, and that's called a baseline separation. Look at the one before that, R is equal to 1. They are partially separated. They are not separated on the baseline. R is equal to 1. But what we want is a separation on the baseline, very well clear separation. This you can achieve only when your resolution becomes 1.5. With more than 1.5, good, no problem. So we tell people to optimize the conditions in such a way that you get a R value of 1.5. And there are different methods also by which you can improve the resolution. And finally, we are coming to the mobile phase carrier gas in the case of GC. GC, we don't have much choice as far as mobile phase is concerned. Mainly 3 different gases are available to us: ultra pure nitrogen, ultra pure hydrogen, and ultra pure helium. Okay. Suppose, actually speaking, hydrogen is supposed to be the best carrier gas for chromatographic separation, GC gas chromatographic separation. But most of the users, they don't use hydrogen because hydrogen, as everyone knows, is a flammable gas. So because you are going to have a column, hydrogen is passing through the column is inside an oven. Suppose there is a minute leakage inside, there is a high temperature. That's a safety hazard. Because it is a flammable gas. That's the reason why people are not preferring to use hydrogen as the mobile phase. The next one is helium. Helium is also good. Next to hydrogen is helium, but helium people don't prefer to use in GC because helium is quite expensive. But that's the only gas we are going to use in GCMS. When you are coming to GCMS, I told helium is the carrier gas what we are going to use. But in the case of GC, we know most of the people use ultra pure nitrogen. So that's the carrier gas what we are going to use. And columns, as I told you, I am again repeating, column is the heart of the system. Columns can be made of different materials. It can be made of stainless steel. That's a metal column. It can be made of glass, or it can be made of fused silica. Okay, there are 3. And columns also are divided into 2 different types: packed columns and capillary columns. Packed columns mean these are all available locally. There are a lot of local people who can pack the column and give you. People are there there are a lot of column manufacturers are there in Mumbai. There will be then Kerala also. So they are locally available column, locally manufactured column. Packing is done locally, and they are quite cheaper also. Price-wise also not expensive. And the length of the pack column, locally available column, can vary from, say, approximately 1 meter to 5 meter. Normally, people use 1 meter or 2 meter column, pack column. It is known as packed column. So there is a packing inside. That is why it's known as a packed column. Then the second type is capillary column. Capillary columns are all imported columns. There is no local manufacturer in our country. All capillary columns for GC are all imported. There are some prominent companies, 5 or 6 companies, worldwide global companies. They are manufacturing all these capillary columns, and we are importing the columns from them. And the starting length is 10 meter. And today we have columns which is more than 100 meter. And look at the internal diameter. It can vary from 0.1 millimeter diameter of the tubing, and you can go to 0.53 mm. So is almost like a hairline, a single hairline that is 0.1 mm. You can imagine what thin tubing it is. So that's a technology. Okay, so and the length is, minimum length is about 10 meter, and it can go to 100 meter or sometimes more than even 100 meter. But all these columns are expensive, and all these columns are important columns. Now, how the selection of column is very critical in chromatography. Whether it is GC or LC, selection of column is very critical. Unless and until you select the right type of column, you will not get the right type of separation. So you have to ask yourself a question whether I should go for a packed column or a capillary column, and what is the stationary phase I should use for my sample, for which I told you should know about the column chemistry and your sample chemistry. What is the stationary phase film thickness? Because the capillary column, I will come to that. You will see that. Now, what is the stationary phase film thickness? What is the column diameter I have to use? In the internal diameter, I told you internal diameter can vary from 0.1, 0.25, 0.32, and 0.53. There are 4 different internal diameter tubings are available. So out of this, which one I should use for my sample? And what is the length of the column? Whether I should go for a 30-meter column, 50-meter column, 75-meter column, or 100-meter column. So what is the length I have to use? So a lot of things you have to decide depending upon your sample and depending upon your applications. So this is an example of a packed column. These are all locally available. In Kerala also it will be available locally. There will be people who will be supplying these columns. And these columns can be either made of glass or it can be made of stainless steel. And you see the stationary phase is packed inside. You can see the packing, and there is something a support material inside. There's a diatomaceous earth that is support material on which your stationary phase is coated. And the support material coated with the stationary phase is packed inside the column. So that is known as a packed column. Okay, and you see the type of peak, the shape of the peak you are going to get on a packed column. At the bottom I have shown one peak shape is a very broad peak. Normally packed columns will not give you a sharp peak. Normally it's a broad peak. You can see that. So because when the peaks are broader, your sensitivity automatically goes down. At the same time, you take a capillary column. You see it's a capillary column. This may be 60 meter or even 75 meter. I mean, the starting from 10 meter, you can get columns up to 100 or more than 100 meter length. So there are different dimensions available. And you see that it's made of either fused silica or nowadays even stainless steel metal capillary columns are also coming. Now the difference between packed column and capillary column is in capillary column, there is no packing. Then you will ask me, where is the stationary phase? You can see the stationary phase is coated inside the tubing as a very, very thin layer. I've shown that as a liquid phase, the blue color, you can see that inside. That's a very thin layer of the stationary phase is coated. And the coating thickness is in terms of micron. That's why I'm coming back to my previous slide. What is the stationary phase film thickness? Today you are getting capillary columns where the thickness can be as low as 0.1 micron, or it can be as high as 5 micron, not more than that. So you have to decide whether I should go for a 0.1 micron coated column or 0.25 micron coated column, 1 micron coated column. You have to decide. Okay, that depends on the sample type, their analytical requirements, and your type of applications, a lot of things are there. And when you're analyzing a capillary or sample on a capillary column, you see the peak shape. You are getting, or most of you are getting a very sharp peak as compared to a very broad peak in the case of a packed column. So that's an advantage. So today, for most of the complex samples, we prefer a capillary column because packed columns will not be very efficient. Okay, so this capillary columns also can be divided into 3 different types depending upon the internal diameter. If the internal diameter of the capillary tubing is 0.1 mm, it is known as a microbore capillary column. And if the internal diameter of the tubing is either 0.25 mm or 0.32 mm, both are called narrow bore capillary column. And if the internal diameter of the tubing is 0.53 mm, it is known as a wide bore capillary column. So you have 3 different types of capillary columns available: microbore capillary column, narrow bore capillary column, wide bore capillary column. You have to decide which is the column you have to use for your sample. Normally we most of the time For many of the samples, we'll be selecting a column in the narrow bore range, narrow bore capillary column, having an internal diameter of 0.25 millimeter or 0.32 millimeter. 0.1 mm capillary columns, that is microbore capillary columns, are used for fast GC analysis or fast GCMS analysis. What is meant by that? You'll see that later. This is a type of capillary column. I just want to spend 2 minutes on this. Main types of capillary columns. There are two different types of capillary columns. One is known as a plot column, PLOT column, porous layer open tubular column. Here you can see inside, that is the left-hand side, the red circle. That's a plot column. So inside, what is the coating? It is not a liquid coating. It's a coating of a solid particle. You remember the first slide I showed you, gas solid chromatography, where the stationary phase is a solid material and the separation is based on adsorption. This is an example for that. So your coating is because of a solid particle. Adsorbent solid particles are coated as a thin film inside the tubing. And that is why it is known as porous layer. All these particles are porous layer, open tubular column, plot column. And most of the time we'll be using this type of column for gas analysis. Because I told you GSE is normally for that particular segment, gas analysis, different types of gas analysis. But the more widely used column is the second one. That's the right-hand side one, the blue color ring, wall-coated open tubular column, or it is known as WCOT column. And here you can see inside there's a yellow ring. That's a thickness, that's a thin layer of your stationary phase, which is an organic liquid, coated as a very, very thin film, where the thickness can vary from, say, 0.1 micron up to around 5 micron. And the inside wall is coated. That is why it is known as wall-coated open tubular column. And that is a one which is predominantly used for most of the applications, whether it is a pharmaceutical application, food technology application, environmental application, perfumery application. We normally go for a wall-coated open tubular column. But when it comes to gas analysis, we prefer a PLOT column, plot column. So plot columns and WCOT columns. There are two major types of capillary column. And what are the stationary phase we are going to use in GC? Most of the time, the stationary phases are polymeric in nature. They're all polymers. And what type of polymers we can use? We can use polysiloxane, that is silicon polymers, or we can use a polyethylene glycol, PG, polyethylene glycol. They're popularly known as PG columns. These are the two major types of stationary phase what we are going to use in GC. Now, when we talk about polysiloxanes, the backbone of the column, the backbone of the stationary phase is nothing but a oxygen-silicon bonding. That's the backbone. We can see that oxygen, silicon. It's a polymeric chain. Now, on this backbone, we can attach different attachments. I have shown R. R is an attachment. It can be a different attachment depending upon different types of columns. If R is if R is equal to 100% the CS3, then we say it is 100% methyl polysiloxane column. It's called a non-polar column, where the separation is based on difference in boiling points. Non-polar columns. Because columns are also divided into non-polar column, medium polar column, and highly polar column. So 100% methyl silicon columns are coming under the heading non-polar columns, where the major effect of separation is based on difference in boiling points. Suppose if you give me tomorrow a mixture of two different solvents having two different boiling points, I will use a methyl silicon column for separating that. I can separate it because of the difference in boiling point. Then if R is equal to cyanopropyl group, CS2, becomes polar in nature because polarity is introduced because of the cyano group, and column becomes a medium polar column. There are different types of columns coming under this cyanopropyl column. Then if it is trifluoropropyl, CS2, CF3, again a highly polar column. I can put R as a phenyl group. It's a phenyl modified methyl silicon column. So depending upon what is the attachment you are going to put on the backbone of the silica, you can get different types of columns having different degrees of polarity. Some may be highly non-polar, some may be highly polar, some may be medium polar, there are different hundreds of columns are available in the case of gas chromatograph. This is an example of a very popular column. You can see it is 5% diphenyl modified, 95% dimethyl polysiloxane column. A very, very widely used column for a variety of samples. 5% diphenyl modified, 95% dimethyl polysiloxane. And because of the 5% diphenyl modification, there's a slight degree of polarity you are introducing. But we normally consider it as a non-polar column. And this can go to 350 degrees maximum temperature. Every column has got a maximum temperature. This can go to 350 degrees, a very high temperature range is available. Then there is something called MS columns. And these type of columns are preferred for mass spectrometry. And here it is, we call it as MS columns, stationary phase MS or low bleed version. Here what bone itself, you can see that. And our attachments are there, but between the inside the backbone itself, we are incorporating a phenyl ring. Or phenyl type groups are incorporated in the backbone of the siloxane polymer. And because of this modification, your stationary phase becomes more stable. You can go to high temperature and low bleeding. And these type of columns are normally preferred when you have a GC-MS analysis, because you want a much more stable column than a normal GC column. That's why these columns are known as DB5MS, RTS5MS. That MS stands for it is a modified column and for better stability. Well, then we are coming to polyethylene glycol columns, highly polar columns. You can see this, there's polyethylene glycol, and there can be different polyethylene glycol columns depending upon the degree of polymerization we are carrying out. And these are also called wax columns. These columns are highly polar columns, and they are preferred for analysis of polar compounds. But please keep in mind, polar columns should be very, very judiciously used. First of all, they cannot go to a very high temperature, maybe maximum to 260 or 275. That's the temperature they can go. Beyond that, it will get degraded. It can degrade. The column can get spoiled. So you have to be very careful with polar columns. Non-polar column, you can use it liberally, but polar columns, you have to be very, very careful. The wax columns or FFP type of columns are all belonging to polar columns. What is FFP? Free fatty acid phase. And free fatty acid phase is nothing but polyethylene glycol, where free hydroxyl groups are esterified by for nitroterephthalic acid. That's an FFP column. And very, very efficient, highly polar columns for polar types of samples. So you have a lot of applications in perfumery industry, flavoring industry for these type of columns. Okay. But at the same time, please understand less stable thermally than most of the polysiloxane columns. The non-polar columns are stable. They can go to high temperature, but these columns cannot. This is a comparison. I'm just skipping this. And sample introduction, in the case of GC, we can analyze gas sample, liquid sample, and solid sample. In the case of HPLC, we can analyze only liquid and solid, but here we can also analyze gas samples. And there are different types of injectors available. If you are purchasing a local column, pack column, then your injector should be a pack column injector. So that is different. But if you are purchasing an imported capillary column, your injector is different. That's known as a capillary column injector. So you have to be very careful which column you are going to use. Accordingly, we have to configure the system. But if you purchase a pack column and you have a capillary column injector, you cannot connect it there. You'll have a problem. So you have to initially decide what is the column you are going to use. Accordingly, we have to configure the instrument and give you. Okay. And under capillary system, there are different types of sample introduction. I will not be going into details. What is split injection mode, splitless injection mode, programmable temperature vaporizer injection mode, direct injection mode, cool on column injection mode. There are different ways in which you can introduce the sample into GC using a capillary column injector. It all depends upon what is your analysis, what is your application, what are you looking for in the sample. So optimizing a GC method is not that easy like a normal UV analysis or a IR analysis. And finally, we are putting the column inside an oven, because oven column is to be heated, the injection. And in the case of GC, there are two different types of analysis. One is known as an isothermal analysis. One is known as a temperature programming analysis. Isothermal means the entire analysis, we are carrying out a constant column temperature. That means during the analysis, we are not changing the column. The column temperature remains constant. That's called isothermal analysis. In the case of HPLC, there is a similar operation which is known as isocratic analysis. Similarly, here, then the second method in GC is temperature programming analysis. That means we are starting for the column, we are starting at a low temperature, maybe 50 degrees or 60 degrees, or sometimes even less than that also. And slowly you raise the temperature and go to a high temperature like 250 degree or 260 degree or whatever it is, or 300 degrees at a constant rate of heating. This is known as temperature programming method. Similarly, in the case of LC also, there is an operation called as gradient operation. There you are actually playing with the polarity. Here actually you are playing with the temperature. That's the difference. Okay. But today for most of the complex samples, we prefer temperature programming method, analysis method. That only can resolve all the components in a very complex multi-component system, like a multi-component pesticide residue analysis or a flavoring compound analysis or a perfumery analysis. I mean, we normally go for a temperature programming method. Finally, we are coming to the detector. There are different detectors available for GC. Whatever is coming out of the column will come to the detector, and the detector will give an electrical signal which is proportional to the concentration of your compound. That's how we are going to do a quantitative analysis. Okay, now detector temperature also should be more than the final column temperature. I have written the sentence as a second sentence. High detector temperature should be set to prevent condensation of sample. Suppose your column is going to 250 degrees, your detector should be 270 degrees, 250 plus 20. Suppose you are going to 300 degrees for your column, your detector should be 320 degrees. Otherwise, sample condensation will take place inside the detector. If condensation takes place inside the detector will get contaminated, sensitivity will reduce, you have to call the service engineer for cleaning it. So to prevent that, you have to always use a high detector temperature. So these are some of the detectors that are very, very common in GC. Flame ionization detector, FID, it is supposed to be one of the most commonly used detectors. Thermal conductivity detector, TCD. Flame thermionic detector, FTD, it is also known as nitrogen phosphorus detector, NPD. FTD and NPD are same in GC. Then flame photometric detector, FPD. Electron capture detector, ECD. And finally, mass spectrometer, MSD, mass spectrometric detector. That's our topic of discussion. Now we are coming to that now. Okay, now we are flame ionization detector, thermal conductivity detector, and mass spectrometer are called as general detectors. They can be used for any type of samples. Whereas the serial number 3, 4, and 5, flame thermionic, flame photometric, and electron capture, they are called selective detectors because they are used only for some certain types of samples, not for all samples. That's why they are called selective detectors, and the other 3 are called general detectors. Okay, where we can use an FID? FID can be used for most of the organic compounds. Any sample which can undergo oxidation in a hydrogen air flame. Now you remember the slide I have shown you. There is a hydrogen cylinder, there is an air cylinder I have shown you, and these cylinders are connected to the detector. We are going to use an FID. So many times, all these detectors like FID will require a flame. And that flame we have to ignite by igniting a mixture of hydrogen and air in the ratio 1:10. 1 part of hydrogen and 10 parts of air. That's the ratio we use. We ignite that flame, and that is required in the detector. That is called flame ionization detector. The sample is going to be ionized in the flame ionization detector. So then ECD is there, but ECD is a selective detector. FID is a general detector. ECD is a selective detector. ECD is very selective to electronegative compounds. Electronegative compound means samples which have got very high degree of affinity for electrons, samples which can attract electrons. Any sample containing halogen atoms is an example for an electrophilic compound. And especially when these compounds are present in extremely low concentration, underline that, extremely low concentration, maybe ppb level or less than ppb level, then only we'll go for ECD. Otherwise, if they are in higher concentration, I can analyze it using FID also. But if they go to very, very trace concentrations, we use electron capture detector. The detector you have to be very careful. It contains a radioactive isotope nickel-63. And then you have to take a lot of precautions. Otherwise, if it gets contaminated, it's a major problem for you. Then we have FTD, flame thermionic detector. It is also known as nitrogen phosphorus detector because it's a very selective detector for samples containing organic nitrogen or phosphorus at extremely low concentration. That's why it is selective to only those type of samples can be analyzed on that. FPD is selective to phosphorus, sulfur, or tin containing compounds, again at very, very, very low concentration. So that is why these three detectors, ECD, FTD, and FPD, are called selective detectors because they can be used only for those type of selected type of compounds, not for all compounds. And thermal conductivity detector is a general purpose detector. Normally, but only drawback with TCD is the sensitivity is not very high. Okay. Anything which is less than 100 ppm or even 50 ppm, it's very difficult to be detected by TCD. But it can detect anything. So once upon a time, we used to consider TCD as a universal detector because it can detect all the compounds except the carrier gas. But today, that universal detector, that position is given to our mass spectrometer. So we are coming to mass spectrometer now. And then qualitative analysis, we can direct comparison of retention time. If a sample is coming at 5 minutes, and if my standard is also coming at 5 minutes, then I can identify the sample. So now, in the case of GC or whether it is LC also, if you want to identify the separated compounds, you should have the respective standards. Without standards, you cannot do qualitative identification, or you cannot do quantification also. I mean, this is common for GC or LC. And there are different types of quantitative analysis available in chromatography: normalization method, corrected area normalization method, absolute calibration curve method. And under this, there are two types called internal standard method and external standard method. So these are all common for whether it's a GC analysis or a LC analysis. Okay. Now we are coming to our today's main topic of advantage of a mass detector. Okay. Now we have seen different types of detectors. We have seen as ECD, FTD, FPD, FID. And when we even talk about that selective detectors, they are all collectively called conventional detectors. And all those conventional detectors are very powerful. Sensitivity, no issue. They are all very sensitive, very, very powerful detectors. But the only drawback with those detectors is they can give a wonderful separation. Suppose my sample contains 10 different compounds, it will give 10 different wonderful peaks. But they will not tell me what is that peak number 1, peak number 2, peak number 3. What are those compounds? It cannot identify. That's a major drawback with conventional detectors. And for identification, it is my responsibility. I have to procure standards, and standards also I have to analyze under the same condition as my sample. Then I have to start comparing the retention time. It becomes my responsibility to identify the separated compounds using reference standards. But many times it is very difficult for you to procure a lot of standards. When I talk about a perfumery compound where it can give 100 or more than 100 peaks, where are you going to get standards for all those? It becomes really difficult. That's a major problem with GC in the case of conventional detectors. And that is a plus point when we talk about GCMS also, because when it comes to GCMS, without the requirement of standards, we can identify the compound. A major advantage. Okay. So while all conventional detectors provide good sensitivity, they fail to identify the separated components on their own. They will not identify. They will give wonderful peak, very sharp peak, very high sensitivity, but I don't know what is that compound. For that, I have to procure standard. So sometimes it is not possible for me, it's not practical for me. Okay. At the same time, an MS detector, if you have a MS mass spectrometer connected to a GC system, it can carry out a very sensitive analysis. Sensitivity here also, there is no issue. We will get a very good sensitivity in the case of MS also. But what is the plus point here? It can qualitatively identify the compound without a standard. That's a major advantage. For qualitatively identifying the compound, you don't require a standard in MS. But then please keep in mind, if you want to do a quantitative analysis, you require standards. The moment you talk about quantification in analytical chemistry, whether it is by chromatography or spectroscopy, you have to create a calibration curve. And calibration curve can be created only using specified standards. So for that, you require standards. In GCMS also, if you want to do quantitative analysis, you require standards. But if you want to do only qualitative analysis, you only want identification, you don't require standards. So be very clear about it. I mean, standards are not required only for qualitative identification, but they are required for quantification. Okay. So now let us come to a very simple definition. What is mass spectrometry? I think this is basically students should understand what is the definition. The basis, I just read it out and I'll explain. The basis of mass spectrometry, MS, is the production of ions that are subsequently separated or filtered according to their mass to charge ratio, and they're all detected. The resulting mass spectrum is a plot of the abundance of the produced ions as a function of the M/Z ratio. What does this statement mean for students? I hope you must have studied this in your curriculum, at least in post-graduation level. My voice is clear. Am I audible? Okay.
Yes, sir.
Hello?
Yes,
Okay.
yes, audible.
Okay. So when you read the first sentence, the basis of MS is the production of ions. From there itself, you can understand the sample has to undergo ionization in the case of mass spectrometer. Because production of ions, the basis of mass spectrometry is the production of ions. This production of ions means your sample molecule has to undergo ionization and it has to produce different ions having various mass numbers. So when my sample molecule undergoes ionization